Okay, so thank you for the introduction. My name is Eduardo, as I was introduced as. And, oops, what's this? Hopefully this works. No? Oh, there we go. Okay, perfect. That's me. I work at Google in the information security engineering team, and mostly what we do is things related to making Google products safer. And recently, I spent a little bit more time, as he said, on CPU and kernel box. And the things that I want to talk about today are related to the ways that we have been approaching the way that we did things internally for Google products to the outside world as well. So our dependencies and open source and hardware dependencies. Technically, what I do at Google is things related to vulnerability stuff, mostly related to vulnerabilities found manually by people. And I don't do it. We have a large team, but I manage one part of the team. So yeah, I was trying to make an agenda, but it was very complicated. So I decided to summarize it as something else, which is simply a goal, which trying to break down how keeping exploit information secret makes offense cheaper, defense more expensive, and how we, as part of developing more secure products, are trying to reverse this trend. And how we are, this is one of the reasons why we're here today, and why we like to engage with the security community, offensive and defensive. I want to start by explaining more or less the information asymmetry example with a very classical example. You might know about it. These are 4 cars, and these 4 cars are all, from the outside they look the same, but one of them has bugs. One of them has problems. I hear that in Singapore it's very expensive to buy cars, actually, but imagine this from a world where people buy very cheap cars. And from the perspective of the seller of the first car, they want to sell it for $50,000, let's say. I don't know if they are a good car or not, but let's assume it is. The second car, the person wants to sell it for a little bit more, $55K. The reason is they both think that's how much the car is worth. The third person thinks it's a little bit cheaper. They want to get rid of it faster. So they sell it for $49K. So the last person, the one that knows they have problems in their car, they can sell it for less, a lot less, because they know the car has problems. But the buyer will not know that the car has problems until a lot later. So they also can sell it for more expensive, because why not? People will be like, I want the best car, and they will just, there's these people that just go sort by price and then get the most expensive. So this is bad, right? This is bad for consumers. This is bad for users. This is bad for everyone. And this is mostly depending on how much people are willing to pay for things. And people are willing to pay depending on the information that they have. So the average price for a car of this size is $52,500. I just added it all and divided by 4. So in the scenario that I gave you, let's imagine that the average price of a car is $52,500. There is one car that is buggy out of 5 cars. But then another person with a car with problems decides, oh, that's actually a pretty good deal. I also want to sell my car, and they will add one more car to the mix. So now there are 2 cars out of 6, and that will lower the price to $50K. Now the problem is that now it is not worth it for some of the people without good cars to sell their cars anymore. So they might remove themselves from the market, which leads to 2 out of 3 cars having bugs. And this is just generally an explanation, like it's called a market for lemons. And it's a general scenario of how information asymmetry from the buyer and the seller can result in market collapse and no incentives to improve. So generally speaking, how could we solve a problem like this? Any ideas?
AI.
Artificial intelligence? Yes, maybe. Maybe transparency as well. So good. The way that I want to express this is that the way that we react to security problems nowadays is mostly as if they were fire or an incident or something that requires immediate attention or immediate response. But that has the consequence of after you are finished with the incident, then you have maybe a slightly bad reputation, a slightly worse product, slower, whatnot. And that is technically not the best way to react to problems. It's a very expensive way to react to problems. And it is generally not good for your business or for your users. A more generally better way to deal with security problems is better to think about it as a medicine problem, which is like rather than eating, free third-party dependencies from Node.js, polyfill.io, and all of these very tasty, high-calorie treats, you might want to eat to do better, maybe things that are not as tasty, like memory-safe languages, or maybe do things that have a clear dependency graph, and things along those lines, like verifiably built systems. And that, generally speaking, is difficult. Like, it makes it, it's less appealing, but it's work. Same for behavioral changes. Like, maybe instead of launching things without testing in production, low coverage of testing and so on, maybe you have to make lifestyle changes like code reviews, or unit tests, or continuous integration, and so on. And all of these type of changes from one thing to another are expensive for developing features. It increases development time, and which are things that developers have to worry about. Developers have to worry about many components of the things that they are working on. Like for shipping features in time, it could be development time, it could be the maintenance of the features that they have, it could be the latency of the applications that they run, bugs that are functional bugs that are introduced by accident, maybe performance. They want to make sure that the applications that they run look and feel fast and are fast for their users, as well as capacity. Maybe there's not a lot of RAM in the cell phones. Maybe there is not a lot of storage on the database to be able to run this. And generally speaking, all of that is what developers are thinking about all the time. So when you say, oh, we want to add some additional features like lifestyle changes or dependency changes, then you are essentially adding time to their development time. You are making them maintain more code. You're adding latency. You are adding more bugs to work on. You are adding additional performance issues, and you are requesting more capacity. So all of that is difficult for you to be able to sell unless you have a good way to measure it. So going to something a little bit more technical, or back to something that maybe is easier to grasp. So can someone spot the bug in this? Where is it? Here. Do you also have it there? Yes. In this, which line do you think has a bug? It's a very simple bug, but this is just an example. Any ideas? The what? Okay, I will not stand there. Fascinating. Okay. The what? On which line? Yes. Yes, exactly. So this field over here is the very simple use of the free. The way it works, very quickly speaking, is that you have a very simple structure. The structure has an allocation somewhere in memory. In this case, I decided memory 4000. It sets the first field to 666. Then it frees the memory, so it is given back to the to the allocator. Then it goes back. Another structure is allocated. It reduces the last previous structure of this allocation implementation. It sets it to 0. And then something is reusing the memory address from before that is supposed to be 0. And it modifies the value, and then instead of being 0 as you expect, it's some other value. And here, what happens is that you have two memory addresses that are pointing to the same thing. Now, this is a very common, simple type of bug. There is a simple fix to all of use after free bugs that you can implement today in your application, which is you go to the libc function, you find libc free, and then you return immediately. This is 100% effective, and it works the following way. You have the same as before, you free it, and when you allocate again, you get a new address. And that's it, no more use after free. The problem with this is that if you run this twice, you start using more and more memory until you have so much memory that you run out of memory. And this is not great, but it fixes the use after free. So the question, generally speaking, will be here: is it worth it to fix use after freeze? Now, it depends. This actually was an extremely useful mitigation for CTF in DEF CON, where you're allowed to do binary diffing, binary patching, and they just modified like the alloc function with, I think, A2 atoy. Well, they just changed the pointer so that it was essentially a node. And for them, it was worth it, right? Like, they get flags for uptime, and the machine was, anytime that there was out of office, it will restart. So, out of memory, it will restart. So then it was actually pretty good for their use case. But if you want to run this on your own organization, it probably will not work out. So the general question is how to calculate when is it worth it and when is it not worth it. So earlier on, I was mentioning the example of responding to issues as an incident, as an emergency. One way that seems to work, or at least historically has worked for us, is to look at the costs that responding to an incident costs. So for example, lost sales or partnerships, or features that you couldn't launch. And then you just ask, or you let the people ask themselves, how would you spend to respond to a given incident? Like you look at actual data, like what actually happened in the past. And you will have like three, generally speaking, like levels. Like how much is the hypothetical maximum you will want to spend, the amount that you actually spent, and if you had implemented certain security mitigations, how much you will have spent otherwise. And let's say with these three categories, you have over time, you plot it over time, how you expect them to change over time. So you can expect that you're going to have, at the rate of introduction of bugs, you're going to have more bugs like this. Or you can expect that, on the other hand, that if you implement certain mitigations, maybe things will get better over time. And you can use that as a mechanism to approximate. This is an example of the Chrome security team, or the V8 security team, actually. How they are looking at comparing two types of mitigations. One is disabling the JIT, the just-in-time compilation just-in-time compilation of JavaScript code in V8, versus the V8 sandbox, which if I have time I will go into later. And generally speaking, the two examples here are looking at previous data. They are looking at in the wild exploits, V8 CTF, which is a setup in which we pay people to write exploits for vulnerabilities in V8. You actually can participate. You don't have to find the bugs. You can just pick a bug from the bug tracker and then implement an exploit for it, and you get paid some money for it. The other one is Pwing, which is a bit more hard to participate, but you can participate as well. There is one part of it that is interesting, which is the in the wild one. As you can see now, thanks to V8 CTF and Pwing, there is actually more data than there would be if we only relied on in the wild exploits. If we only relied on in the wild exploits, then we will have way less information, and we might reach the wrong conclusions. So as you can see, there is some sort of a trend on JIT compilation being actually very, very effective for in general, but not so effective compared to in the wild exploits. Versus the sandbox bypass that is just generally speaking effective as compared to the other. So the more data that the V8 security team has, the easier it is for them to defend or invest in different areas, especially on mitigations that have some amount of cost, development cost or maintenance cost, like the V8 sandbox does. I want to shift a little bit into the in the wild area that I'm talking about here. And the one way to think about it is that because of the way that technology is affecting our lives right now, it is very common for everyone to use it, including good guys, bad guys, all types of guys and girls. And law enforcement and intelligence community are struggling to keep up with this. And the way that they are, 10 years ago, James Comey, the FBI director, was calling for backdoors for encryption. And at the end of the day, he made a very compelling argument about why law enforcement needs this information. However, one of the things that happened at the end is that one of the things that happened after all is that we have the government, intelligence community, become another participant in the market for 0 days before. However, it's not just law enforcement, it's also military use. And it's not just the military use of one country, it's the military use of multiple countries. This is just like continents, but you can imagine. And it's not just law enforcement from one country, it's law enforcement from every country. And it's not just law enforcement, it's also private investigation and stuff. It's also not just that, it's also like bad guys, folks like cyber criminals and so on. And generally speaking, you can think of every time that someone is trying to reach, let's say, the treasure. Every time someone is trying to play the bug or whatever, they will try to take multiple paths. And the more paths that are taken, the less likely it is that they will take the same amount of area. Simply because from a perspective of you have to select to go right or left. You have to select, you might assume that something is hard, but actually it's not hard. And depending on your previous experiences and your skills at certain areas, you might choose different areas, leading to multiple types of reaching the same end result. Which at the end looks something like this. So as you can see here, the top 2 folks took the same path at the beginning, but then almost everyone else went a different way. And then when a defender is trying to figure this out, they have a better knowledge of the system, so they will take the most straight path. And the most straight path might not always be the most effective. Well, not always be the most effective one to stop all of the other actual adversaries. So for this case, let's say that defense sets up a couple areas, that a couple mitigations along the way, but they actually are not that effective against real adversaries. Generally speaking, you can think about this as a form of cost. So in the scenario that offense needs a certain amount of information, defense needs to know as much information as offense to be able to have a fair fight. However, it becomes more expensive because there's more demand and there's more competition, and it also becomes harder and more expensive for defense to afford this information, simply because they have less supply, less information. And the reason there's less supply is because it's harder. So it just becomes more expensive. So the general concept is how to increase offense without increasing defense costs. And we can also use artificial intelligence, but in this case, we can say it's transparency. And generally speaking, the idea is that by publicly talking about ways to solve these very difficult technical problems, we can attract offense to use those problems, those mechanisms. And they don't have to, but they can. Because from their perspective, they can use what is going to work. But then this will also make it easier for us to make it worth it to invest in certain mitigations. However, as soon as you start investing in these mitigations, then people will start choosing the other paths, right? They will be like, okay, I'm not going to use the path that you know is going to be detected, then you use the other one. But then it just becomes a money problem. Then you have to decide, do you use the very cheap path that comes for free, or do you choose the more expensive path that you have to figure out yourself? And this also becomes a problem in the case that if there is a lot more information public, then the vulnerability clusters, the exploitation techniques and primitives are also likely to be, they are not infinite, they are limited. So the more people that are publicly talking about this, the more likely it is that you're going to have duplicates and you're going to have collisions, and it's more likely that things are going to eventually get shut down. So then from the perspective of talking to research, you have going from one defender. If you are talking with the public, then you have many defenders that kind of balance the situation with you. As a form of comparison, you can see what we did for the kernel CTF. This is the number of public kernel exploits according to multiple sources. I duplicated them and added them together. And you can see in 2016, when Dirty Cow came out, there was a big a big interest spike, and then since then it kind of died down. Then we started launching kernel CTF, and then that started going up again. So now we have more kernel exploits public than we ever had before. And one of the things that we're trying to do with this area is to go from the current status, where we have quite a lot of very expensive, it is very expensive to get this information because we have so much competition, to a situation like hopefully in the future, let's say 10 years from now, there is a lot more researchers, a lot more people that are able to do this just because it is a lot easier. The barrier to entry is not so high. And also is, hopefully if we are doing a good job with mitigation, it's also a lot harder to do reliable exploits. And it's also harder for offense to like profit from this scenario. So in the ideal long-term scenario, the ideal scenario would be that it goes from the current scenario where it's very profitable to do offense to something where it's not so profitable to do offense. Like, of course, it's never going to cross like this. It's this is an ideal scenario. Yeah. So the ideal goal of this presentation was to try to break down why keeping information secret made offense cheaper, different, more expensive, and reversing the strength. And the premise is that with transparency, buyers can differentiate more secure products, which means that they can demand better from their vendors. It also allows defenders to quantify their mitigations, and by the way, increasing the cost of offense and lower the cost for defense. And hopefully this whole mess that I presented at the beginning kind of makes a little bit more sense. And I don't know how much time I actually have. So if I don't know how much time I have. Cool.
Thank you, Eduardo. I think we have some time left for Q&A. Anyone have any questions?
Hey, so speaking about making it more expensive for attackers and cheaper for defenders, when you're rolling out Miracle Pointer and Chromium?
Where is Miracle Pointer? I didn't mention Miracle Pointer. That's so sad. I thought I did. I ended up choosing something else. I think it's already there, but I'm not sure if it's enabled in all platforms. As far as I know, it's enabled in some platforms, but not in all of them. Or maybe it's enabled in all of them. I'm not sure. Is it not enabled in all of them? It's enabled in some of them for sure, but there's a chance that it's missing in some obscure architecture. I don't know.
Hi, thank you for the talk. The part about the market forces in disrupting the industry, more or less. From your experience, from Google's context, does increasing bug bounty actually help disrupt the market for the offensive security side, or was counterproductive because it drives prices up? Like from your experience, should Google increase bug bounties for LCs, etc.?
I mean, I think it depends on what you do with the information. So once you have a bounty program, when you increase the prices, you most likely are going to receive more reports. But then if you don't do anything with the reports that you receive, then then nothing happens. Yeah, there's going to be the same amount of bugs that. Maybe this is a good way to think about it. So you have if you have renewable bugs. So if the bugs that you fix are slower than the rate that you're introducing them, then it's irrelevant how much you pay. But if you are removing bugs from the code base faster than they are being introduced, then it is more likely that you're actually making a difference. So I would imagine that if you are increasing prices without doing anything with information, then it is not going to disrupt anything. But if you are, even with a small amount of information, if you're doing something about it, then yeah, you will eventually make an effect. But you usually need a lot of information to be able to make good investment decisions. And the investment decisions usually are very expensive. So that's why more information, usually that's why, so for kernel CTF, we increase the rewards 10 times from 10,000 to 100 something thousand. And the reason was because we needed a lot more information than the one we had.
Thanks for your sharing. Yeah, I think I briefly saw your slides. I think it wasn't covered in the main sharing part, like in your appendix, like there was a slide on like rewriting binder from C to Rust. Yeah, so actually, like for my school project, I had a project converting like C code to Rust. I think it was pretty difficult. I just wanted to like know your thoughts about like moving forward, like with like the conversion to Rust, right? Like with everything like supposedly memory safe, so we will fully eliminate this class of like memory bugs. Like, what's your thoughts on it?
Yeah, so one of the advantages of Rust is that it definitely, and not just Rust and Golang and even Java, like they remove a certain type of problems. And there is, one of the things that I wanted to mention in this slide that I didn't, these are backup slides, is that you can eliminate problems. And by eliminating problems or class of problems, this is the most effective way of improving security, just by eliminating the problem completely. And yeah, Rust eliminates that problem. And it is, however, the most expensive thing to do. So re-implementing code is highly difficult. And even from the, I don't think I have the code here, but well, I have a part of the code. But if you find the patch series that Alice posted on the Linux kernel mailing list, she actually goes into talking about like the trade-offs of rewriting code. And actually, the first sentence of the commit of the patch series of the intro letter was that this is usually the last thing that you want to do. But it is worth it for certain scenarios, especially in something as critical as binder that is accessible even from sandbox processes. That was very important for them to tackle. Also, like it also had also other reasons, like the code was very hard to maintain because it was very complex and there was a lot of technical debt. So yeah, it made sense for them to do it.
Hi, so, sorry I asked. So, no, I really like the fact that you presented the trade-off analysis on like how increasing certain variables right, would decrease the cost in defense, right? But is there any empirical studies or like statistical studies done in Google that really shows that there's a statistical significance in these areas that you guys have explored? Or is it just based on observations or what?
Yeah, I mean, I think it's interesting. To be able to find enough data, we will probably need a couple of hundred years of information. So maybe in a couple of hundred years, we can talk about it. But the number of vulnerabilities and exploits that we have and information that we have is coming at such a slow rate that is mostly something based on principles, but we will only be able to essentially measure it with error bars and degrees of freedom and so on. Once we have like enough data that the amount of error rate is easy to measure. But that will take a really long time. I think it's probably possible for certain types of bugs that were super common and were well studied. But whether to say, like there's also problems about like what you can measure and what you cannot measure. And it will be hard right now to be able to make it. But it's something we looked at, or at least I looked into. But it's not immediately obvious. Like at least for certain parts of it, you can actually do. So for this part, like the rate of introduction of bugs versus, at least for the bugs that people know how to find, you can see how that goes to zero if you make certain changes. I mean, it becomes obvious. Like if you're protecting against use of the free box and then you're switching to binder, you will have no more use of the free box. And then that, of course, it goes from something to zero. It's very clear to measure. But yeah, to be able to do a general analysis that says that in general, for every possible case, this will work. They will have statistical significance. That will take a very long time to be able to have that. The market is too low.
Hi. Great talk, thank you. I was curious if you had any thoughts on like increasing the access or the transparency and like having all these sort of end days effectively visible. It's obviously a trade-off because there's going to be like cyber criminals and other people who now have access to these, and then time to patch I think very apparently with like Android and also some like many other platforms is pretty long, like on the order of months, if not years, for like weird edge network devices and stuff like that. So I was curious if you had any thoughts on like what the trade-off of this increasing transparency versus people having a lot more access to easily applicable end-date chains.
Yeah, I think these are the problem here is twofold, which I'll try to split it. One of them is increasing the time to deploy, which is, increasing the time to deploy. The time to deploy will be, once the bug is public, how much does it take for it to reach the user deploy? And that increases or decreases the shelf life of the vulnerability. And yeah, you are correct that if an exploit is public, and by the way, all of the kernel CTF submissions are public. So there is a Linux kernel exploit for pretty much any kernel, always public in our GitHub. Ooh. And yeah, there is definitely.
Hello, hi. Oops.
Hello.
Can you hear me? I can't hear anything. Mic.
I suspect this is the next stuff. Anyway, I'll try to quickly finish this. The time to deploy is.
Okay. Can you hear me?
Yes, I can hear you. Okay. All right. Time to deploy. Yes. So generally speaking, if the number of bugs if the supply of bugs was very limited, then I will agree that disclosing the few bugs that exist and an exploit for them will have a very meaningful effect on the market. However, with the assumption that the bugs are easy to find and are very diverse, then the trade-off will be whether to have more information to be able to accelerate progress or to restrict it to be afraid of it being used for evil. This is different for cases when the software is open source, like the Linux kernel, where actually the community needs to know this information to be able to make timely changes, versus when the code is not open source, and then the only people that can meaningfully make a difference with technical details are like secret. And then in those cases, then it's still useful to have transparency from the perspective of metrics and exploitation paths that might allow the user to understand how to protect themselves despite the vendor's action or inaction. But yeah, that is the trade-off. The trade-off is mostly about what information to be made public and when, and what considers unreasonable risk. Unreasonable risk being risk that is like unexpected versus risk that users are understood and expect that will come from them. And generally speaking, like the only way that we can reduce the patch gap, the patch gap being the time to deploy, is if we put pressure as consumers on the manufacturers that give us this code to create the mechanisms to update and to do it quickly. And they will never do that if the information is kept away from the users. So I guess the aspect is like the more information we can provide pressure to the market to deliver these results is the better. And this of course creates short-term versus long-term. Okay, I think I need to stop because someone is talking. All right, thank you very much.